Burning down cities. Hell of a topic. I'm going to give you the bottom line up front on this one because it feels a little sensational. So, the attack I'm going to present is viable, but it is based on infrastructure that is not yet deployed today. So, there's time to prevent it. And that's really what I'm here for, is to discuss with you, this amazing audience of highly skilled folks, how do we stop something like this from happening? Can we prevent cities from being burnt down by the future that we're headed towards? I believe we can, and that's the goal we're going to talk about today. We're going to cover how do you actually do something like burn down a city. We're going to look at some alternatives, and I'm going to leave you guys with a plea to find a different way. Before we get into that, just a couple of disclaimers. I want you to read these with the same amount of attention that you read all the T's and C's of every website you visit. When I originally pitched this talk, Los Angeles was not burning down. Obviously, a little bit's changed since then. The tone of my talk is going to be a little bit more somber because of what happened. It is a tragic example of how quickly fire can spread and how quickly it can overwhelm the departments that fight that fire. The numbers on my screen are probably a little bit out of date. That was when I originally turned in my final presentation, but they're pretty close. So that gives you an idea how devastating of an incident we're talking about. And what we're going to present and go over today is a bigger fire than what this was. So what's our target system? This is going to be your IoT and IIoT devices that are in homes and businesses. We're looking at a new system through the meters that connect to customers' Wi-Fi, so their existing Wi-Fi infrastructure, to issue commands and controls directly to those smart devices. Centralized command and control of what could be millions of smart devices in a metropolitan area. There's some things I want to mention that are not part of this presentation. To be honest, there's a lot of ways that we're going to be able to burn down cities in the not too distant future through cyber attacks. They deserve their own presentations, but that's using smart inverters or utility scale battery storage to cause fires or other catastrophic incidents. So the attack. We're going to go into this in more detail, but just from a high level to begin with, we're utilizing known vulnerabilities. So we didn't create any 0 days for this. We were just looking at published stuff that's already out there. This audience is probably pretty aware that IoT devices are pretty vulnerable, that there's a significant number of them. Things like smart ovens, for example, that have very poor controls on what you can set their heating elements to. When we look at saturation, based on market research of a few metropolitan areas, these are percentages that represent the vulnerable IoT devices within that market. Those are metropolitan areas. So 22.9% of structures in Los Angeles contain one or more vulnerable IoT device. We're looking at basically a 5% success rate for this attack. A lot of the research that we found was higher, around 15% success rate. By success rate, I mean you cause the device to catch on fire. But at only 5% at that market saturation, in those markets, those are the numbers of simultaneous or roughly simultaneous structure fires that you can cause. So in the greater Los Angeles area, that's 17,862 simultaneous structure fires. We're going to dive into an example using Fort Worth here a little bit later. This is our attack chain. The stuff on the left side shouldn't be too new to this audience. A lot of it's been around for a pretty long time. We're going to touch on those briefly. Stuff on the right, that's our new stuff that doesn't exist today, our infrastructure that will be coming out, and we're going to go into that with a little more detail. The walled garden approach. Nothing new to anyone here, but for a long time, grid security was based on the idea of isolation. We've known that there's a lot of vulnerabilities in grid control software. That hasn't changed. That's nothing new. Hopefully nothing new to anyone here. But we always based it off of isolation. I've always made the argument that was never real security to begin with, but nowadays it's gone. Between DERMs, cloud services, and now even AIs, we're connecting grid control to more and more systems that we never have before. And now we even have companies that are tied to foreign actors that are establishing direct control into our direct connections into our control systems And they're doing that by buying up third-party generation. So we have foreign actors who buy third-party generation who have direct connections into the FEPs of our control systems. That gives them a back door into a system that has a lot of known vulnerabilities. And the new thing that we are introducing in this section is that these meters will be connected directly to customer Wi-Fi. Now, you might be able to run a firewall or something like that on these meters, but other than that, there's going to be no infiltration protection other than what's provided by the ISP. I mean, this audience might have a little bit more protection on their home networks, but the vast majority of customers, it's just a straight router to the rest of the world. The exploits. So again, shouldn't be new to this audience. The existing grid control systems have a lot of available exploits. Tens of thousands, in many cases, of known CVEs. Many of them are highly exploitable. But an attacker won't even need to get to those because most of this software has built-in attack features. And when I say that, I mean things like code execution or privilege escalation built right in as a feature of the product. And I'm not knocking vendors for that. That's a whole different talk. It's a culmination of 30 years of requests from utilities to add those features that got them there. There's also a big lack of patching in this industry. Again, it's not a knock on the vendors. These legacy systems are a culmination of 30 years worth of code. Trying to patch a 30-year-old library and not break everything else in your system is an immense challenge, and I don't envy them the position that they're in. All right, so the new bits. The centralized control. This is the heart of our attack. What's going to be introduced in the not too distant future is a control system that is able to communicate to all of the enrolled IoT devices within a network. It is the customer's responsibility to enroll those devices. I would assume it would be optional. I would be a little surprised if someone came out with a non-optional enrollment. But that's how we're going to get to these systems, a centralized control. The other challenge that we're introducing is that we're putting an advanced compute environment into meters that will be on the sides of customers' houses for 20 years. And we have to maintain an advanced compute environment for 20 years. That's a hell of a challenge, I'm sure anyone here knows. That edge compute environment, other than whatever firewall is built into it, is going to have that direct connection to the internet, making it highly vulnerable. One thing we're not talking about here is a bot network of millions of meters. That's a whole different talk. This is an untested solution, by the way. No one's doing this today, at least not that I'm aware of. So we don't have anything to really point to look at how successful this could be. And there's going to be a real big challenge going forward with this. As that meter infrastructure ages, we're not going to be able to run modernized security controls on it. Imagine trying to run today's security controls on access points built 20 years ago. So the actual exploit to the end device. Again, these are existing things, published research that's out there. I've been advised not to talk about specific brands, so I'm going to leave those names out. But it's all out there, easily available. IoT devices, look up setting them on fire. When we look at things like the ovens, smart ovens have actually removed a lot of the mechanical safeties that they had. So if the firmware commands the relay on, the heating element stays on until that relay turns off. And once the external of the oven reaches approximately 500 degrees, it auto-ignites the wood cabinetry that it's contained within, and the house burns down. US battery, or UPS batteries, there's a whole flood of these inexpensive UPS batteries. You can buy them on Amazon now. They're Wi-Fi connected, and there's a really good published research on changing the firmware to cause thermal runaways. The one thing that we are looking at that's a little bit new is these smart meters themselves have pretty large capacitors in them. And we're attempting to modify the firmware to cause them to overload and explode. That one is new. If that works out, I might be here next year talking about that. We'll see. So we only need a small percentage of these devices to fail to a point of starting a fire. But we can use inverters, and this is different from using the inverter itself to start the fire, to increase our likelihood by creating a lot of reactive power within the network, causing electrical fires to be much more likely. If you find yourself asking, well, if these are all existing exploits, why can't someone do this today? Well, a threat actor could, but they don't have that centralized control that we talked about. So they might be able to do it on a small scale. Let's say they compromise some vendor cloud. They could attack all of those. but they're not likely going to be able to get every device within a metropolitan area. So that's the big change, is that centralized control that we're possibly providing a threat actor. So before I get into the scenarios, I do want to present an alternative solution right up front. So we don't necessarily need to put Wi-Fi on the meters. There are other ways that we could get to these smart devices. We could issue commands to them through their manufacturer's cloud. Most of the smart devices out there communicate with a cloud from the manufacturer. Many of those manufacturer clouds have APIs available. We could issue commands to our cloud-based systems that then work with those APIs to get the control messages down to the smart devices. This gives us a lot stronger infrastructure that we can secure long term. While the commands are still being issued, they're passing through the manufacturer first. We're not issuing direct commands to the devices themselves. An alternative option is an application for people's smart hubs. Many smart devices are controlled via a hub, and those hubs support applications. We could develop our own app that integrates with those. The customers would still get the benefits of the demand response and the time of use incentives that are going to come along with this, but I believe that we would be significantly reducing the likelihood of a successful attack. The other big advantage that we get is we're not going to be trying to run security on infrastructure that has to last 20 years. So how do we crash a manufacturing system? And we're going to go into a specific example of this on the next slide, but the first thing is you have to wait for their enrollment. Again, it doesn't exist today. We don't have manufacturers out there with IIoT devices enrolled within our ability to get responses from them or controls to them. After they're enrolled, you have to compromise the meter. Because they're an individual attack, a targeted attack, not a broad spectrum attack, the meter itself can be compromised directly through its Wi-Fi connection, or it could come from the centralized command and control. But the meter, again, aging quite a lot, could be your entry point for this attack. You'll have to identify your target devices. That could be something as simple as causing a power outage. You can just command open the meter itself, turn the power off, which isn't devastating, but it's pretty expensive for most manufacturing facilities. You can influence their wireless I/O, which is the example we're going to get into next. And once you have that target device, you can issue your malicious commands, or you can use commands that are completely normal, which would be harder to detect, things that you would expect to see but have bad results. I do want to point out that good security controls, good security hygiene, if you will, could help prevent this attack. Not a lot of manufacturing places that I've had the privilege of doing security analysis on have that kind of control. But if you whitelisted commands and that kind of things, you could stop something like this. The target must have a vulnerable device as well. So if we look at a specific example, at a chemical processing plant, if a company has enrolled their temperature sensor, it provides the utility forecasting data. The reason we'd need this, right, is that in the future, which we'll talk about here a little bit more in more detail, but just to provide context for this example, utilities are going to need the ability to forecast energy demand on a granular level, seconds, instead of minutes or hours. And to do that, one of the ways they foresee an ability to have that forecasting is to be able to see the energy demand of individual appliances, or in this case, manufacturing processes. That gives them that ability to predict how much energy they need 5 seconds from now. And we'll get a bit more into that, but the threat actor identifies that temperature sensor, and they use a legitimate command and control message to change the sensor's calibration. For those of you who are familiar with chemical processing, this is going to be a really bad scenario. Once that sensor is wrong, once it's no longer able to correctly read the temperature of whatever process that is, the system can overheat. In chemical processing, that's bad. Our best case outcome is emergency shutdown. Our worst case outcome is an explosion. Hopefully, most manufacturing facilities would have redundant systems, and an emergency shutdown would be caused, and the worst that would happen is they lose a batch of their chemicals. Explosions are not good. So how do you target a high-profile individual? We're talking politicians, celebrities, those kind of folks. This is, again, you have to wait for them as the individual to be enrolled. They have to have a device that's compromisable. You have to compromise that meter. It could be direct again, or it could be through a command and control centralized system. You'll want to pick your attack. That can be a localized power outage, which then you can lead to a break-in or other things. Or a lot of higher profile houses have home battery backups, which a lot of them, again, available research, you can cause thermal runaways on. They'll issue those malicious commands using those known vulnerabilities to accomplish the attack, whether that's breaking in or burning down the house. All right, so the big one. How do you burn down a whole city? We can't do it today. Again, that's the good news. And that's what we're here to really try to focus on, is how do we stop us from getting there? But let's say you have enough customers who have enrolled their IoT devices into the utilities program using customer-facing Wi-Fi out of the meters that are now in their house. Your attacker is going to choose their path. What do they want to do? Do they want to attack smart ovens, space heaters, toaster ovens? There's a lot of options to catch on fire. It's actually surprising, a little concerning, to be honest. And when we look at some things like smart ovens, it's actually surprising to me that we've seen the mechanical controls that prevent them from catching on fire removed. And they're just relying on the firmware. It turns a relay on and off. I assume that's for cost savings, but who knows? Either way, the devices are out there. So they choose their path, they pick their devices. Once they've compromised that command and control system, using one of those attacks that we talked about earlier, getting to the vulnerable centralized control, they can issue malicious commands to every single device within the target area. So every device enrolled in the utilities centralized control could have a malicious command issued to it simultaneously. If they created a dirty enough power, reactive power using inverters, if there's a large amount of inverters within that control network, they're going to increase their likelihood of success. But we're going to find out real quickly that it doesn't matter too much. So our Fort Worth example. Again, the tone of this has changed a little bit. Originally, I used Los Angeles as an example, just to be candid with you all. Then Los Angeles caught fire. It changed our math, fundamentally. My models got updated based on what we saw, based on what we learned from that fire. And now here's an example using Fort Worth. So the attacker sees that there's high winds in the forecast. This is key for success. Without high winds, the fire doesn't spread particularly well, and the high winds prevent firefighting from the air. If you want fires to spread, and you want them to go out of control, you have to prevent air support. If we look at that 5% success rate, which again, success rate of research is higher to 15%, but we went with 5% because there's a lot of unknowns. That's still 3,258 structure fires caused near simultaneously within the Fort Worth area. Fort Worth has 50 engines. It takes 2 or 3 engines to fight a fire. So if they're fully staffed, which staffing is a big challenge, but assuming they're fully staffed, they got some volunteers coming in. They could fight roughly 21 fires simultaneously. They bring in support from nearby Dallas, that's 60 additional engines. Now they can fight 45 fires simultaneously. Well, 45 is a whole hell of a lot less than 3,258. Let's assume our success rate's significantly lower, 10% of that 5%, 325 fires. That's still a lot bigger number than 45. And that's what we really started to look at when we built out these scenarios is, oh, you can overwhelm fire departments really quickly. In fact, your average metropolitan area, for those of you who took the poll, can fight a fire simultaneously in roughly 0.005% of their structures. You hit a number higher than that, and you've overwhelmed them. They can't fight the fire anymore, and that's exactly what we saw in Los Angeles. At some point, There's a lot of blame going around. People are blaming the fire department, but honestly, there just simply wasn't enough water. If you open every single fire hydrant in a metropolitan area, they're not gonna work. You lose water pressure. So when you have that many structures on fire, it becomes an unfightable scenario. And that's what we're seeing in this, and that's what I want you all to help me prevent. So this seems like a crazy risk. You have to find yourself asking, do utilities really need to have command and control over IoT devices? I know that's the question I asked when they first told me that's what they were gonna do. I was like, let's not do that. That sounds crazy to me. Well, as I found out, it's not gonna be an option for much longer. Today we don't have this, and today we don't particularly need it. But we are gonna need it in the future. The reality is, we cannot build the power grid fast enough to meet the change in demand and the change in supply. With the rollout of EVs, with homes using more and more energy all the time, the transmission and distribution system simply isn't prepared to be able to provide that energy to everyone, and we can't build it to get there in the time that we need it. To complicate that, the entire model of energy distribution is changing. We don't generate in a centralized location and distribute out from there anymore. Now we're looking at generation distributed throughout our network and flowing in every direction. Our grid wasn't built for that. That's the harsh reality. So we're adapting it to it. And that's the direction we're headed in. And it's not gonna become an option much longer for us to not have demand response and forecasting down to the individual appliance level. Obviously, that's not gonna be done by humans, it's all gonna be done by software, but that's the direction we're headed in. And that's what I'm imploring all of you to think about today, is if this isn't an option, this is the direction that I'm being told we have to go in. We have to have that level of forecasting and demand response. How do we do it securely? Can we use the cloud as I presented a little bit earlier, or applications on hubs? Or is there ideas that this audience is thinking of that I haven't thought of? If we have to have that level of control, if we have to have centralized control of millions of IoT devices that we know are vulnerable, how do we prevent a city from burning down? And that's what I want you all to leave with. Prevent cities from burning down. Questions?
With modern urban planning, why not use fire breaks? We have a tendency to try to maximize use of real estate by putting houses like 8 feet from each other now. And if we were to create bigger gaps between homes, or at least preserve the ones that we have in our building codes and not keep getting them closer and closer, then we would limit the spread of fire. So while you might be able to set a whole bunch of individual homes on fire in a development, you might not lose the whole development if you had bigger fire gaps. And you could do this in a systematic way throughout an urban area, including with buildings. Stop trying to maximize your real estate and start trying to maximize your fire breaks.
I think I got all that. I'm just now discovering it's actually really hard to hear you guys because I get a weird echo up here. If I understood the question correctly, it's way out of my scope. I can tell you how a cyber attacker would attack a place, but as far as like fire gaps between houses, talk to the cities. I think I understood your question. If I didn't, I'm sorry. Although you could probably ask it again because yeah. There's not a line, so we're in no rush.
Hi, my name is Robert. On the devices, the IoT devices, are you seeing any standard bodies like the UL certification bodies to build in safety instead of having a firmware-only type of mechanism?
Yeah, so some devices definitely have that. The challenge that we saw when we started doing research for this about a year and a half ago is that that's not what people buy per se. There's been an explosion of IoT devices that are very inexpensive, that are not particularly well developed, that folks are buying off of online retail places, and they're highly vulnerable. But I don't want to, there are ones that are UL listed as well that are well-known brands, that are $12,000 smart ovens that are just as easy to set on fire. I think that we probably need to have better controls over it. I think that, it probably is a good idea to say that a smart oven should have a mechanical override. So if your heating element gets to 700 degrees, it shuts down. It would prevent a lot of problems, but it doesn't seem to exist today. Yeah.
Just thinking about the change management challenge introduced, I mean, I could see so many benefits of being able to do demand forecasting in a more granular way and demand side management. So I'm all on board. But I'm thinking about making sure that those devices are updated not only to support grid integrity, but also from a security perspective. It's a challenge we have just in a factory or any OT asset. Have you thought about some of the ways that could be navigated in a pragmatic means?
Sure. Yeah, well, I think a big challenge is that the vast majority of the devices are already out there today. I mean, we saw the market saturations earlier, roughly in the 20% for any given metropolitan area. And what that means is that there is a vulnerable device in 20% of the structures in any given metropolitan area already there today. So I think there's a big challenge with that. Yes.
That was an excellent presentation. I think it was a good way to open up the first day. So good job on that. You did say one thing that would help to increase security would be going through the manufacturer's cloud, but I think that would still require a Wi-Fi connection or connection. So I was wondering if you could just go in, since we have a couple minutes, if you could just go into a little bit more detail about what you mean by that.
Sure. I don't have a couple of minutes, but I do have a few seconds. So the devices are already connected to Wi-Fi. That's how they work. That's how a smart device works. Most of the devices that we've seen connect to a manufacturer's cloud. So again, I've been advised not to mention any brands, but your typical smart thermostat, for example, connects to the cloud that is made by the manufacturer. It issues commands to them. Those clouds have available APIs so that other apps can integrate with that product, and that's what we would be integrating with, is the API of the manufacturer's system instead of directly to the device itself. So the manufacturer could have controls over what goes up there. All right. Thank you, everyone.